Hi. So today I'm going to be using this very poorly and hastily made document camera setup that I have going here to try to record a lecture about the chain rule, and I'm going to apologize in advance because this is really poorly done. I apologize. But we're just going to do the best we can with this. So today we're going to talk about the chain rule. So the chain rule is like the product rule and the quotient rule in that it's a rule that we use to differentiate certain kinds of functions. And in particular, it's going to be types of functions where they're a little bit more complicated. So it's going to be something where you have a composition of two functions, one function plugged into another function, for example. So suppose we want to take the derivative of the function f of x equals sine of something more complicated than just x. Okay, so let's say we had a polynomial inside, like 12x cubed minus 8x squared plus 7x minus 5. Right? Okay, so we know that the derivative of sine of just plain x is cosine of x. And so you might be tempted to say something like, okay, well the derivative of this would be cosine of this whole polynomial. Or maybe you would say the derivative of this should be cosine of the derivative of the polynomial. But it turns out that neither of those are actually true. If you want to take the derivative of this composition of functions, right, this sine of another polynomial function, we have to use something called the chain rule. The chain rule says that if you have a function f of x, which is a composition of two other functions. So let's say that it's a function u of x plugged into the larger function g of x. And if those two functions g and u are differentiable, right, if their derivatives exist, then we have that the derivative of f of x is equal to the derivative of g with respect to the inside function u of x times u prime of x. All right, so let's go through what this means. What we're saying is we're taking the derivative of the outer function g with respect to the inner function. So if we're going back to this function up here, we would take the derivative of the sine function with respect to the polynomial. So we'd keep the inside the same, but then in the end, we're going to multiply by the derivative of the inside function. Okay, essentially what this comes down to is the fact that the derivative of f with respect to x can be thought of as the derivative of your outer function g with respect to u, so dg du means the derivative of g with respect to u, times the derivative of u with respect to x. Right, that's this part here, and then the du dx, that's this part here. Okay, so let's go through this example of what we just did. Apply this chain rule to our first example here and see what we get. Okay, so let's see. Our original function in example 1 was sine of 12x cubed minus 8x squared plus 7x minus 5. Okay, so we're plugging this polynomial function into the sine function. So our inner function here, right, the smaller function that's being plugged in is the polynomial function. So what we're going to do is we're going to call this our u function. Right, everything in here, this u of x, is the polynomial 12x cubed minus 8x squared plus 7x minus 5. Now I need to know the derivative of that because I know I'm going to have to multiply by u prime of x. This is simple enough. Using the power rule, the derivative would be 36x squared minus 16x plus 7. Okay, so once I have the scratch work done, what I'm going to do is go back and rewrite my f function as a function of u. So it's sine of the u of x function. Right, it's sine of that polynomial, which we're now calling u of x. So according to the chain rule, to take the derivative of f, I need to take the derivative of g, that's the derivative of sine, with respect to u of x, and then multiply by u prime of x. So f prime of x is going to be, the derivative of sine would be cosine with respect to that u of x, And finally, the chain rule says then we multiply by u prime of x. Right? This looks a little convoluted. Don't worry, it'll get easier the more you practice it. Okay, so now all we do is plug back in what we have so that our function in the end is back in terms of x's instead of u's. So instead of cosine of u of x, now we'll write it as cosine of the original u function. 12x cubed minus 8x squared plus 7x minus 5. And then in the end, we have to multiply that by u prime of x. That's the derivative we found up above. 36x squared minus 16x plus 7. All right, and that's our derivative according to the chain rule. It looks pretty messy, but the more you practice it, the easier it'll get. So let's do a couple of more examples here. Okay, so let's do something like this. Example 2. Let's try to differentiate the function f of x equals 7x cubed minus e to the x raised to the 6th power. Okay, so we technically don't really need to use the chain rule here because, right, this is just a function being raised to the 6th power. We could write out 6 different copies of it, FOIL over and over and over again, and take the derivative of what's left, right? But we don't actually want to do that because that would be a lot of work and it would be really messy. So it makes more sense for us to try to use the chain rule here. So the first thing that we want to do when we're using the chain rule is identify our inner function. So the inner function in our case is this stuff that's inside the parentheses. Right? It's easy to find the inner function because it's often in a set of parentheses, or it's underneath a radical sign, or it's inside some kind of a trig function. So our u of x here is inside these parentheses. It's 7x cubed minus e to the x. I know that I'm going to need to take the derivative of that, so the derivative is, let's see, 21x squared, and the derivative of negative e to the x is still negative e to the x. Okay, so now I'm going to go back, rewrite my original function f of x as this inner function u of x raised to the 6th power. Now, according to the chain rule, to find the derivative of f, I take the derivative of this function with respect to u of x, and then I multiply by u of x. All right, so the power rule says we'd bring that 6 down in front as a coefficient, leave the inside alone, raise it to the 6 minus 1 power, so to the 5th power, and then multiply it by the derivative of the inner function, multiply it by u prime. And now what we do, just go right back, plug in our original u of x function, and then multiply by u prime of x. So this would give us 6 times 7x cubed minus e to the x raised to the 5th power, and then we multiply that by u prime of x, 21x squared minus e to the x. Okay, all right, notice if we look back at our original function and then look at eventually what we got for our derivative, what happened was our exponent got moved down in front as a coefficient, right? 6 got moved down as a coefficient. The inside stayed the same. We raised it to the power of the original 6 minus 1, and then we multiplied by the derivative of the inside function. All right, all of the scratch work in the middle is just sort of to keep track of what we're doing for now, but eventually you'll do this enough and you won't have to go through all these steps. You'll be able to do this in your head. All right, let's do one more example. Let's say we wanted to find the derivative of differentiate means find the derivative of the function square root of 4x to the 5th power minus 3 cubed. Okay, so there's sort of a lot going on here. We could think about this as actually a composition of more than 2 functions here. We can think about this 4x to the 5th minus 3 being plugged into the cubic function, which is then being plugged into the square root function, but that's sort of a messy way to look at it. So before we actually go on with differentiating this using the chain rule, it might make sense to get rid of that radical sign using an exponent and then just apply the chain rule once. So I can rewrite this as 4x to the 5th minus 3 cubed, and then the whole thing is being raised to the 1/2 power. Right, when we change a radical to an exponent, its square root becomes a 1/2 power. And I can multiply my two exponents together to rewrite this one more time as 4x to the 5th minus 3 raised to the power of 3 times a half, or 3/2. Okay, right, that's my original function. I haven't used the chain rule yet. I haven't taken the derivative yet. But to take the derivative, what we're going to do is identify our inside function. Of course, that's going to be 4x to the 5th minus 3. That's the stuff inside the parentheses, so we'll call that u. U prime then would be the derivative of u, which is 20x to the 4th. And that's it. The derivative of a constant is 0. So now I'm going to go back, rewrite my function f of x as u of x, raised to the 3/2 power, and then apply the chain rule. So according to the chain rule, the derivative is going to be the derivative of this with respect to u times u prime. So 3/2 times u of x to the 3/2 minus 1 power. 3/2 minus 1 would be 1/2. Then we multiply that by u prime of x. Okay, plug everything back in again, and we'll get that the derivative is 3/2 times 4x to the 5th power minus 3, all raised to the 1/2, and then we'll multiply that by u prime, which is 20x to the 4th power. And if you want to simplify this in some way, maybe you want to multiply the 3/2 times the 20x to the 4th, you can, but you don't have to, right? There's no need to unless it's useful for some particular reason. All right, so I'll do another video with some more extra examples of the chain rule. It can get more complicated than this. Sometimes you'll have to apply the chain rule multiple times, but we'll do more practice.